And here is the plan for today. Here. We're going to take a look at equipotential surfaces. Again, you know what those are. You know what the electric field lines are. We're just going to have a better mathematically accurate representation of what those are. That way, you can determine those, in the development of electricity and magnetism or electromagnetic theory. All of these things were extremely important because you could then determine how charges are going to flow once you know the potential surfaces and electric field lines, right? So since we just introduced the concept of electric potential, a class before the exam, and then we looked at the so-called Earnshaw theorem that tells us that in a given volume, if there are no charges in that volume, then the maxima or minima of that potential function can only be on the boundaries, not inside. Otherwise, it leads to a discrepancy, if you will. And then we also pointed out that for the potential, the reference is arbitrary. Yeah, I'm going to change my audio device a little bit. I can hear better. Okay. So let's take a look at now a equipotential surface. Now, why is it a surface? It's kind of easy to see because we're describing a volume, and in that given volume, we're fixing the value of the potential to some value 50. And so this is going to give you a family of 2D surfaces. It's like in the 3D space, if you fix the distance from the origin, you have one condition that you add, then you get a two-dimensional surface, which is the surface of the sphere. Okay, so that's how that process sort of work. Now, I think we haven't seen this. We have defined the electric field as the negative gradient of the potential, but we haven't done the inverse relation so far. Does anybody know what the inverse relation looks like? Anybody? The inverse relation actually comes from the nature of the force field, which is called conservative, right? I'm sure you have heard the term conservative. The Coulomb force is conservative. What does that mean? Does anybody have any thoughts on what we mean by a conservative force field?
The corollary will be 0, right? If I remember correctly.
So let's fix the 2 points, R1 and R2. What we mean by conservative is if you take a test charge along path 1 from R1 to R2, or you take the same test charge along path R1 to R2, the lower path, you get the work done to be exactly 0. It only depends on the endpoints, not the path, right? So the path independence, this just basically means work is path So I don't know whether it was Malik or Juan who said this. If you complete the loop, you go from R1 to R2 along one path, come back on the other path, you are going to get the total work done to be 0, right? So the work done by the electrostatic force when you go from, let's say, R1 to R2 is going to be Q from R1 to R2. It's going to be naturally an integral along the path dl dotted with E. Everybody with me so far? Okay, and then now we can replace E with negative gradient of phi. Okay, and so when we do that, you get negative Q R1 to R2 dl dotted with gradient of phi. And whenever you are taking a dot product of a certain vector element with the gradient, it just gives you the derivative of that along that direction. And so if you integrate the derivative, all that you are going to get is the quantity back. So this becomes phi of R2 minus phi of R1. I'm not being consistent with my choice of the lettering for phi, but that's okay. Then you get the sign. This phi and that phi, they are exactly the same, right? They're exactly the same. So don't confuse, right? So the work done can now be written in terms of phi of R2 minus phi of R1, right? So it's a difference in the electrostatic potential that we just introduced is what gives us the work done, right? And so if you have a closed contour on a cycle, you go from R1 to R2 along one path, return on another path. Then you have a closed contour, and then you're going to get dl dotted with E. When you have a closed contour, you can use the Stokes theorem, right? Because you can then look at the curl along the flux of the curl on the surface that is bounded by this contour, and that is going to give you 0 because curl of E is 0, right? So this is the conservative nature, right? Any other example which leads to a conservative force field? I mean, anybody remembers something else that's conservative?
Gravitational force field.
Can you say that again?
Gravitational force field.
Gravitational force. Yes, very good. So that's another conservative force field, right? But this allows us to actually use some, define a reference point. Remember we said for the potential, the values don't matter. It's the derivative that's important. And so we can define a reference point in such a way that phi of R0 is 0, right? But what it allows us to do is write down this phi r with respect to some reference point as a negative integral of R0 to R dl dotted with E. So you take a unit test charge and you move it along the any path does not matter, from R0 to R1, and you calculate this integral dl dotted with E, and that gives you the expression for the potential. So from here onwards, we are now able to invert that gradient relation, and we identify the potential to be the work done on a unit test charge from some reference point R0 to the current point, right? So that's now, if you only know the electric field, this is how you can determine the electric potential. Everybody with me so far? So now once we know this, we can actually use it to define the equipotential lines and correspondingly the electric field lines. So let's take now a equipotential surface. I'm just going to draw one imaginary one here. And so let's say that's the equipotential surface. I wanted to make it circular. It will let me. There we go. So that's, let's say, example equipotential surface. And we want to take 2 points One is here R1, another one is at some arbitrary location R2. Both of them lie on the equipotential surface. So if that's the case, what is going to be phi of R2 minus phi of R1 is going to be 0, right? Because they both have exactly the same value. That means the integral from R1 to R2 dl dotted with E, the sign does not matter here, is going to be 0 as well, right? Everybody agrees? So that the integral of the dl dotted with E, so dl is this tiny element along that equipotential surface that you're just taking. And of course, you have, again, multitude of paths available. Okay. Everybody with me? So if you are traveling along the equipotential surface, dl dotted with E along any path on that equipotential surface is 0. So what does that mean? What's the physical meaning of this? Anybody? You can feel free to unmute yourself and tell me the answer. And I want somebody else other than Malik to speak.
GL and electric field E are perpendicular with each other.
Okay, so that's one possibility. E is perpendicular to DL. Any other thoughts? Anybody else?
E equals 0.
Equal to 0. Okay, very good. Everybody with that, everybody agrees with those two possibilities to give you DL dot equal to 0. So this one we're going to take a look at now. Of course, the expression that we wrote down is path independent, and so this actually is not just has to be perpendicular to DL, it has to be valid at all surface points. And so this is E, it's actually more general than that. It needs to be more general than that. So E is perpendicular to the equipotential surface. Okay, and so that's the at all points. That's the implication of that. Equal to 0 is a special case. You may not always have that, right? There may be some special cases where that might work, right? And so then, yes, somebody had a question.
Yeah, for this equipotential surface, the source of electric field E should be at the center.
Yeah, for this one, because I just draw, it's easy for me to draw a spherical surface, so that's why I did, right?
So electric field, that is the source of electric field, is at the center of that surface, right?
It doesn't have to be exactly at the center. I may have a spherically symmetric charge distribution of any kind. It does not need to be a point charge. Does that make sense?
Okay.
Yeah. So there is no restriction that it needs to, at least in this case, as long as you have a spherically symmetric charge distribution, you're going to get a spherically symmetric equipotential surfaces and radially outwards electric field. So that's an easy, simple situation. But what we are trying to do is develop a mathematical framework for doing this in any kind of general case, right? So we need to be able to visualize this. So what we do is we need to define our electric field line. We figured out the direction of the electric field on the equipotential surface. But what happens if you veer away from that equipotential surface? Which direction should we be going? So electric field line is a continuous curve drawn so that the differential element of, say, arc length dl. Remember, this is not necessarily a straight line. That's why it's arc length dl points in the direction of E of R at all points at on that line, right? And so then you can write down the dl along the electric field line. So that's a definition now of an electric field line. It's going to be proportional to the electric field. So some coefficient times this at all points, right? And dl itself is actually a function of r, right? Because the line element could change as you move away, move at different positions from this. So these are the ideas that allow you to figure out find the equipotential surface, pick out the value. Let's see, where did we talk about it? Right here. Pick the value of the potential. That's going to give you the surface. And once you know that, then you can do that. And as you change phi, it's going to have so that's why it's called the family of surfaces. And then you have these electric field lines that are always going to be perpendicular to those, right? So these are the ideas that allow you to figure out the electric field lines and equipotential surfaces. And Maxwell and Faraday both at that time, if you look at if you try to think about historically what they were doing at that time, was the whole physics at that time was dominated by study of Newtonian mechanics. And so everything, even when Faraday and Maxwell studied electromagnetism, they were always trying to look for a mechanical model of things. Okay, and so that is something that you can always may find very strange right now, but we are bound to the prevalent knowledge of the time, and then you start making progress from that. So if you were to read some of Maxwell's treatise on his displacement current and the complicated mechanical models that he has, there are discussions of that in the book. Make sure you read through that. That will tell you historically how we have come to the current understanding. It's not obvious. It's not even the way we describe things in the textbook. That's not always have been how we thought about it, right? That thinking develops, evolves, and that is something that you also want to be always incorporating in your work. Keep thinking all the time. It's not the way you're thinking is you may think, okay, physics is already standard, everybody knows how these things are done. Not really, right? You can always come up with new ways of thinking about it, and that can lead you to new insights. And so you should never ignore that sort of a thing. So let's just take a quick example of, let's say, a charge density that's like Anup was saying, a charge sitting at the origin. So Q delta R, you can calculate the potential due to this, which is going to be Q over 4 pi epsilon 0, 1 over R. So it drops as you go farther away, but it doesn't drop as 1 over R squared. Equipotential surfaces. Anybody can tell me the shape of the equipotential surface? Anybody? Concentric. Right? And of different. Yes. Miriam? Was there Miriam or
It
Fatima?
would be spherical.
Spherical, right. So these would be spherical shells, and concentric, right? So you have different values of the radius, we'll have different size of the shells and so on. Now we want to find out the electric field lines. So electric field lines are radially inwards or outwards. Are radially inwards if Q is less than 0, and outwards if Q is greater than 0, right? Everybody agrees that just because of the size of the charge, right? But if you want to do some more general calculation, then you can actually write down a differential equation for the electric field lines using this. So dl, remember, is equal to lambda and E. Now you could take a look at the Cartesian components of this. So dx is going to be, so the thing with this lambda is the lambda has to be now constant in all directions. And so what this leads you to is dx over ex should have the same value as dy over ey and should have the same value as dz over ez, right? Because what we have done is dl is dx x hat, dy y hat, dz z hat, and e is ex x hat, ey y hat, ez z hat, right? And then all of that is going to be equal to lambda. And then these would give you the electric field lines if you could find the analytical solutions of this, right? So the are the electric field lines. And once you found the electric field lines, then you have essentially determined the electric field because you can figure out how the charges are going to move. So this is kind of how Maxwell did all of these things, right? So it turns out though that this particular method does not guarantee analytical solution. So the solutions are rare. So you kind of do heuristic, you don't exactly have closed form expressions, but numerically you can still use these techniques to evaluate electric field lines. Okay, and then you can take a look at the figure in the book for a couple of different examples of the electric field lines you should try to practice. So I can give you a few charge configurations, and then you try to find the electric field lines, right? So that is something that you do practice. So this is for practice. And the first one is, let's say you have a charge Q here, and here you have negative charge 2Q. These kinds of things get tricky. If you just have positive charge Q and the negative charge Q, that's going to be straightforward. Or let's say you have a equipotential surface here, phi equal to 0, and then you have a charge negative Q sitting in front of it. These kinds of configurations. So that's A, that's B. I'll just give you those two and try to figure out a way to draw the equipotential surfaces and the electric field lines. Okay, so that's a task for you, and you can use Mathematica if you like. Mathematica has a couple of important, a couple of useful functions. If we get time towards the end of the class, I will introduce those functions to you. And then you can try to use Mathematica to figure these kinds of things out. Of course, again, it's not, you of course need to know how to calculate the potentials and then introduce some constant values for them to figure out the equipotential surfaces, and then calculate the gradient that gives you the electric field, and then you calculate the electric field line. So it's not straightforward. Even these kinds of things, if you want to do them precisely, take a lot of work, right? So there is some work involved there. We won't go into that today. Let me see what is the next topic. So solid angles, okay. Any questions anybody has so far on this? So solid angle concept is important because it gives you sort of a deeper understanding of the Gauss's law. And so let's take a look at that now. Let me first find out if you guys know what solid angle is. How to define solid angle mathematically precisely. If anybody knows, please speak up. It's a geometrical concept, and let's me see if I can draw a little diagram here to illustrate what's happening. Any thoughts anybody has so far? No? Okay. So I have some random surface here. I'm going to shade it. It's a 3D surface, so it's not necessarily spherically symmetric. It may have, random kinks and stuff. What we want to do is find the solid angle projected by this at point O. Okay, why would we need that? Need that because, if you're going to sum over the charge distributions, that's one of the first thing that you have to do in the volume integral. Okay, so we're going to take maybe 2 points that are along the boundary here. Okay, so those are the boundaries. And it is as if we get a tiny image of the surface over here. On the unit sphere, right? So the radius of this is 1. That's important. It's a unit sphere. So, and then let's take a look at the position of some arbitrary point on that surface. So each point on that surface has a position vector, and all of those position vectors are going to pass through or cut through this unit sphere. And if you have this, you basically kind of animate that that position vector over the whole surface, it will cut through a picture that kind of I have shown here, right? So that's the projection of the. So let's label this. That is omega s. That's the solid angle of this surface S projected onto the unit sphere. Okay, so let's first okay, so these things are called rays, and like I said, you can think of rays emanating from O, so that they basically cover the whole area of this surface S that's given there. And so they're just basically going around and covering all of that, and that just basically maybe, let's say, creates a shadow, if you will, of this surface on the unit sphere, and that we are trying to find the area of that shadow, right? That's what the purpose is. That's essentially the solid angle. Okay, so yes.
As I know, in astronomy, maybe solid angle is how much flux density we are getting, and it's a ratio between flux density and the intensity. Is this?
Right, so this is a geometric property, right? So we are only looking at the geometry there, and then the solid angle has a variety of different applications in different areas, right? So since we're talking about the rays, light rays would be similar, right? And so it would have the application like you saw. So what what you are looking at solid angle as a ratio of intensities is actually what we are doing right now is turning it around. We're trying to figure out solid angle geometrically, and then you can connect it with variety of different things. So anytime you have a 1/r² type variation of something, light intensity is like that, gravity behaves like that, and electric field behaves like that, then you are going to have a usefulness of solid angle. It's going to depend on the solid angle, as you will see here in a minute. Does that make sense? Okay, so it's geometric property of the three-dimensional space that we live in, right? So omega s is the solid angle subtended by S at O. So you need the area, some area that's given to you, and the origin. The origin is also important here. Let's see. And how do we define that? Is the part of the area of a unit sphere centered at O. So whatever I said verbally, I'm just writing it out here. That is cut off. So you can think of a very bright laser that's coming out from the outward region, let's say, from the and the area blocks that laser, but the area that's not blocked is going to cause the laser to pass through, and it's going to make a cut on the unit sphere by the rays. Okay, there we go. So another way to think about this is project every element ds of that surface, which you can write it as ds times n hat, onto the direction rs minus r. So let's actually define what is rs and what is r. So for this, we have a origin of the coordinate system is somewhere else, so O prime is the origin. I'm going to use a different color for the position vector. So the position of the point O, along which we are trying to find the projection. I wonder why this wants to move. Let me just move the point O there then. And then that is the position vector R of the center of the unit sphere, and the position vector of a point on the surface is going to be rs. And so the vector that joins the 2 points, the origin and a point on the surface, is going to be rs minus r. Right, so everybody with me over there? And then what we want to do is look at, I'm going to draw this vector with a dashed line that continues over here. This vector. So something that starts from the origin and it just radially outwards, that is going to be in the direction of rs minus r. So this is really speaking a unit vector in the direction of rs minus r, but I'm going to write it like this. Right, for any, we don't have anything more compact than that, right? So that's how we can write down that unit vector in the direction of this rs minus r vector, and the unit vector that is perpendicular to the surface at that position is not necessarily along that. It has to be tilted somewhere else, right? So there is now 2 vectors, and we want to look at the angle between the two. So the projection there is going to be important. So the area may be, this is the unit surface, right? The area may be tilted. So that area, when you look at its shadow is going to be reduced, right? So the shadow depends on the dot product of the two vectors. So let's take a look at now mathematically what this is going to do. Okay, I think I did not complete this sentence here. So project every element ds onto the direction rs minus r. So it's just projecting, divide by, we need to, by the square of the distance. Why do we have to divide by the square of the distance? Because of the projection onto the unit sphere. Right? That's how far it is. Farther we are, the shadow is going to get smaller, right? And the amount by which it's going to get smaller, it's going to be 1 over r squared, right? And so then we can now define, write down everything mathematically. Omega s at a position r, which is the center of the unit sphere, is going to be, you do the solid angle for each small element on the surface. So this is basically sum over all of the RS values, and that is going to be now BS. That's the small surface area there, times R minus RS over R minus RS cubed, right? Because we are dividing by the distance squared, and then you need to multiply it by the unit vector, and so that's why you have the power of 3 there. And you can kind of begin to see now this behavior is similar to what we get for the Coulomb's law, and so that's why the connection, Coulomb's law, is essentially actually geometric in that sense. Similar things you can do for any inverse square law force, or a quantity that behaves like 1 over r squared, which is light intensity. You can think of this as applicable to light intensity as well. Okay, so that's the definition. Now let's take a look at a couple of simple cases. And this one is, so one observation. Omega SR changes sign when the observation point which is R, right, passes through the surface S, right? Because that's going to change R minus RS, right? The sign is going to be reversed if you go, to the other direction. So what happens is ds does not change the sign, and this should be a dot product because there are two vectors. ds does not change the sign, then the normal vector stays the same, but r minus rs, instead of radially outward, it will be radially inwards if you are on the other side of that surface. So if this O point was somewhere here, the projection would have a different value there as opposed to this. So as it passes through that, you get this. So let's now take look at a couple of implications of that. Okay, then I think we need to also point out the convention. If the sign is going to change, you need to define which sign is positive. And the one sign is fixed, so the direction of R minus RS is taken to be positive when the curvature of S tends to enclose the point R, the observation point. So you want a curved surface that's enclosing. And if you're outside of that, So if you have a spherical shell, for example, you're trying to find the solid angle for that, you are inside, it's going to be positive. If you're outside, it's going to be negative. Okay, so that's going to be important. Now there is a little bit of there is a pole for you. So I'm going to draw two surfaces and you and an observation point, and then you have to tell me what's the solid angle for those, right? Now solid angle for, let's see, another observation, let's add this, solid angle for and for a fully enclosed surface like a spherical shell is, anybody knows what that is? I think you know the answer to this already. At a point
Why?
inside,
A by r square.
at a point, it is an angle, so it cannot have any dimensions. Somebody said 4 pi or something related to 4 pi.
It's a
Yes, it's 4
4
pi.
pi.
4 pi.
Yeah.
Okay, very good. So that's 4 pi. You know that already, right? So now let's draw a couple of situations, situation A, situation B, and then you're going to tell me what the solid angle is going to be. And so we have this kind of a surface, and I'm going to shade it so you know what the surface looks like. Now this is, of course, I'm drawing it on a flat plane. This may not completely lie in that plane. It may have areas that are coming out of the plane. But now let's take a look at the observation point O to be here, and to just help you figure this thing out. That's O. Right, so there are different areas here. So that's the total volume, and the volume is enclosed by the surface S, and we're trying to find the okay. So it's now a closed surface that's enclosing a certain volume, not a sphere now, it's some arbitrary shape. What is the omega S for this one? That's the question. And in the meantime, I will draw another picture here. So keep thinking about it. So think about A while I draw the picture for B. It's a completely enclosed surface, right? So if you in the first case, you're outside of it. In the second case, you are inside of it. So that the diagram I'm drawing here, you are inside of that volume. And no, it doesn't do that. Okay, let me do this. Very good. Any thoughts anybody has? Okay, I'm going to label these 1, 2, 3, and 4. So let's simplify this a little bit. You just tell me what would be the solid angle due to 1. Surface 1, right? So it's you. We actually gave you a larger thing there, right? A complete volume that's enclosed by a surface S. You're only taking a look at a tiny component of it, right? So there's the shaded one. What is going to be the solid angle or comparatively, what's the solid angle of 1 and 2? And 3 and 4, the magnitude wise. Magnitude wise, all of them are going to be exactly the same, or are they going to be different? Let me just let's just see if you get the point. Is it going to be same? So omega s due to 1,
With 0.
omega s is equal to 2. Are they going to be the same magnitude wise? Let's first answer this question.
I think yes.
I think yeah.
Same.
Yeah,
Okay.
that's why I
Okay. So
told
looks like everybody kind of agrees that the projection, right? Because the limiting rays are the same, right? That are covering the whole surface, and so the distance doesn't matter. You know, the farther you are, you're dividing by a larger amount, and so even though the area for 4 seems larger because it's getting divided by 1 over r squared, it has exactly the same solid angle as the one that's closer at 1. Okay, everybody with me on that? Okay, so all of those solid angles have the same magnitude. The directions are different, right? So for 1, is it going to be positive or negative? The surface is kind of enclosing O, enclosing the observation point. So it's going to be positive. For 2, it's on the outside, so it's going to be negative. 3 positive, 4 negative, all of them same value, and so they're going to cancel each other, right? Except for the sign. And for O here, for in part B, again, those 3 shaded surface areas have exactly the same solid angle, but the first one is positive, second negative, so they cancel each other out, and only the one outside that counts, right? So that means if you're inside the volume, okay, inside the volume, doesn't matter what shape your volume has, the solid angle omega s is always going to be 4 pi. So this is shape independent. And that's something that's crucial and important about it. And if you are outside of that volume, does not matter what is that shape of the volume or whether it is spherically symmetric or not, you are going to get the total solid angle to be 0, right? So outside, observation point is outside, and observation point is inside. Let's highlight this. So for outside, solid angle is always 0. If the point of observation is inside, the solid angle is always 4 pi. Everybody with me? And it does not matter. There's no spherical symmetry needed for this. And that's what allows us to do these, essentially allows us to derive Gauss's law, if you will. Right? So we can mathematically write down omega s is ds r hat over r squared over the whole surface is going to be 4 pi if the observation point is part of the volume and is equal to 0 if observation point does not belong to the volume. Okay, that's that. And so connecting this with Gauss's law, if you look at the flux, right, and this now connects, this is similar to what Muriam was talking about, the intensity fluxes. The flux in the electric flux passing through a surface, it is going to be ds dotted with E, right? So that's simple. That's just the definition of flux. And that is going to be equal to Q over 4 pi epsilon 0 times the solid angle, right? So you have now the 1 over r squared dependence in the Coulomb's law comes from this geometrical property actually of the solid angle. So we wouldn't be surprised, we shouldn't be surprised if we don't find departure from Coulomb's law 1 over r squared, right? So the r squared plus epsilon, that epsilon needs to be essentially 0 because it's now a property of the 3D space that we live in, right? It comes from the geometrical property solid angle that we have. Okay, everybody with me? And it of course
Dr.
comes
Kapale?
from the, yes.
What is the unit for this solid angle?
So what do you think will be the unit for the solid angle?
No, I'm still searching this question.
Okay, so you take a look at the integral definition, right? Take a look at this. What's the unit of 4 pi?
It will be radian.
Yeah, well, the unit that's used, it's actually angle, so it doesn't have any physical dimensions. But for solid angles, it's steradians. That's the unit that's used, right? But that's the important thing for us in physics. You know what? It doesn't matter what you call it. It needs to be a dimensionless quantity. There should be no thing of, you know, and you can kind of see that here, right? ds is length square. You are dividing it by a length square, and it's just r hat integral, right? So you know you're going to get a quantity that does not have any physical dimension. The name steradian, you know, that's just the name that you give it to. It's strictly speaking, it's not a unit, right? Because it's a dimensionless quantity, really. So you could take sine of that angle, right? Sine of that angle, that's allowed, because it's a dimensionless quantity. Everybody with me so far? Makes sense? Let me see what we were going to study after this. So give me just a second. I'm going to scroll quickly. So we did the solid angle. Let's take a look at quickly electrostatic potential energy. And then we will, if time permits, we will do the Green's reciprocity relation. If not, we will do it in the next class. So let's take a look. We already talked about the work done, right? When you have a charge moving in the electric field. So let's see, we're going to talk about. I'm just going to say PE, potential energy, and the potential energy change. If you know from mechanics, is the work done on the object, negative F dot ds, right? F, then you can write it as negative, so delta V, let's just do kind of infinitesimals, not derivatives, delta V over delta S, which is essentially negative gradient of V, negative gradient of some potential, right? So the change in the potential energy. And if you now connect, so this is from mechanics, right? We know this. And so similar ideas work for the electrostatic situations as well. Now let's connect this with the Coulomb force. F is Q times E, and you know that E is negative gradient of phi, and so the F is going to be negative Q gradient of phi. So you can already begin to see that the electric potential energy is going to be Q times phi, because F is equal to negative gradient of VE, right? And so you connect those two, the electrostatic potential energy is going to be, so this is the electrostatic potential energy. Of the charge Q. So you can figure these things out just from analogy with mechanics and how things work there. And then this. Now, of course, this is just a simplified picture of what can really happen. You may not really have a single charge. You may have two charge distributions. One we call ρ2 of R, and the phi 1 is coming because of some other charge distribution, ρ1 of R, right? And so phi 1 itself be coming from d cube R 1 over 4 pi epsilon 0 ρ1 of R over R, right? Okay. And you do this, you calculate it, put it in there. So it's like having the potential. Now you can calculate the electrostatic potential energy of two charge distributions that are right next to each other. Okay. And there are some other things that you can do, which is the force, Coulomb force can be written as partial derivative of the electrostatic potential energy with respect to S. That's the some coordinate, right? Some direction along which you're trying to find the force. Then it's going to be just the integral d cube R rho 2 of R E1 of R. So you know these two relations are kind of connected with each other for from the obvious relation between E and phi. Any questions anybody has? Okay, so there is a little jump here, conceptual, so we will not do that yet. I'm going to ask you to read, so this is a reading assignment. That takes these definition that we talked about and looks at a discrete collection of charges in 3.6 for electrostatic total energy. And it does both the discrete function first, and then it goes into the continuous domain. And so what do I mean by discrete? So if you have a charge distribution and you want to find out what's the total energy of that charge distribution, because if you bring in one test charge, all the charges that are already there are going to create this effective electrostatic potential. And so this charge, the incoming charge potential energy depends on what's already there, right? So the configuration matters. How you are building your charge distribution is important. For the first charge that's coming in, it's essentially free because there's no electric field that it has to oppose. Then the second one coming in, it has to interact with the first one. The third one coming in is interacting with both of those and so on, right? So you have to do the summation, double summation over the charges that are already there and another summation for the charges that are coming in. And so go through that, it's straightforward. You may have seen it before, but that gives you total energy of any given charge distribution, right? So I'm just going to write down the final expression here. So total energy of a discrete charge distribution, it comes out to be 1 over 4 pi epsilon 0. There is a factor of half. This one you will need to pay attention to why that is. So you need some thinking to do there. And then you have two summations equal to 1 to n and j not equal to I all the way up to n. And then the interaction is like the Coulomb force, except the denominator is not 1 over r minus ri minus rj squared. It's just 1 over ri minus rj, right? Because that's the potential energy. And so it's equal to just half of the qi times phi of ri summation over I equal to 1 to n. Okay, so this half factor is important, right? So it's not just because you have n charges, you don't just individually calculate the potential and do qi phi ri. That doesn't work, right? That's how it. And then of course, if you can extend this to now a continuous charge distribution scenario, where also you have this extra factor of half. So it's not 1 over 4 pi epsilon 0. It is 1 over 8 pi epsilon 0. And then you, of course, have the integral over the two charge distributions, one at R and the other one at R prime over the distance R minus R prime. Or you can write that as half d cube R rho of R phi of R. So the potential at each point, and then you do the summation over that, right? So this is, of course, the effective potential from the whole charge distribution. And so this gives you the electrostatic total energy of any collection of charges. It is similar. You can write down similar expressions, if you will, for the for a massive object, if you do the summation over all of the component masses and add it all together, similar idea works there. But you need to think about, where is that factor of half coming in, right? Now, the thing to note here is if you look at this expression, phi can be negative and rho can be negative as well, right? In some cases. So it turns out from just by looking at this expression, you cannot tell whether UE will be positive or negative. And it turns out UE is always positive definite. So it can be always greater than or equal to 0. And the way that works is, let's just take one mathematical step to figure this out. So 1/2 epsilon 0 integral of d cube r okay, let me see, where is this coming from? Let me add a couple of steps here. We start with this, and then we introduce the definition of, so let's say negative half d cube r rho of r. Phi is going to be now see. First, we need to use Gauss's law. So Gauss's law is going to be this. So rho over rho divergence of E is equal to rho over epsilon 0. So I'm going to bring in epsilon 0 here. And then I'm going to replace this rho of r by divergence of E multiplied by phi of r. Okay. And then what we do is integration by parts. And we assume, of course, the finite charge distribution. So the electric fields and the electric potential at faraway points is 0. So the boundary term is gone. You know how integration by parts works. It's integral u dv is equal to uv minus integral v du. Okay, so that's the idea. And then when we do all of that, it turns out we get 1/2 epsilon 0 integral of d cube r. We move this derivative to phi from E, so it just stays as E dotted with gradient of phi, and then so that's and the one of the other term that remains, which would have a positive sign, is PQR. So it's basically the UV type term is divergence of phi E. Okay. And so this thing gives us 0 because E of r goes to 0 as r goes to infinity. So I told you about that. And so what you are left with is u of E equal to, let's substitute gradient of phi as negative of E. And so you're left with the positive, right? Negative and this negative sign. In the first term, they turn into positive, and you're then essentially left with d cube r E squared, right? And this you could see its absolute value of E is that what matters, not so even if you have a negative charge distribution, the whole total charge in that charge distribution is negative, still the total electrical energy of that charge distribution is going to be positive because it depends essentially on the absolute value of the E squared. And then of course the integration, right? You have to sum over all of the electric fields like that. Okay, so that's how that works. So that's complete discussion of the electrostatic energy. Of course, you have to supplement it with a reading of section 3.6 to understand that factor of half. But you sort of get the idea of what's happening here. So that's conceptually kind of important to see that. Now we do have a few minutes, so we can go back to the last topic, which was the Green's reciprocity theorem or Green's reciprocity relation. And anybody has any questions before I start talking about that? Okay, no questions.
Could you please explain once this last thing we are doing this? Because actually I didn't get all these things.
Yeah, I skipped a few steps, right? So here I use the divergence theorem.
Yeah.
Right, like this to replace the charge density, which can be positive or negative, with electric field. And then we do the same thing again. We do integration by parts, right? So you have this divergence of E, right? So let's take a look at this. Divergence of E times phi is going to be the derivative applied to E phi minus the derivative E dotted with gradient phi, right? This one you agree with?
Yeah.
Right? So just use this, integrate on all sides, and that's what you get. So the left-hand side that you have, right, the single term that you have is now converted into two terms after the idea of integration by parts. And then one of the term goes to zero, right? The boundary term always goes to zero, which is the second term. And so even here, it looks like the first term, it is negative, but remember it includes a gradient of phi, which is negative of the E. And so the negative sign goes away and you basically have E squared. Does that help?
Yeah, thank you.
Okay, so I skipped a few steps, but it is something you could figure out, right? Very straightforward there. Okay, so let's recall the definition of the electric potential for a charge distribution. And I'm calling it definition because it essentially comes from the Coulomb's law. Right, so just the charge distribution, integral over the charge distribution divided by the distance, right? Now let's take a look at two situations. You have two charge distributions, rho 1, and that causes phi 1 of r, and another charge distribution, rho 2. And let's say these are not overlapping. They are, slightly separate. It actually does not matter even if they're overlapping or not. And so you have a charge distribution, rho 1, that creates a potential, phi 1, and charge distribution, rho 2, that creates a potential, phi 2. Okay. Now let's take a specific combination of the two, right? So we want to, let's say, find out the potential energy of the charge distribution rho 2 due to the field caused by the charge distribution rho 1, right? So that's how you would write that down. And this would then look like 1 over 4 pi epsilon 0 integral d cube r integral d cube r prime now, because I want to completely expand out what phi 1 looks like. And so you are going to have rho 2 of r times rho 1 of r prime divided by the distance r minus R prime magnitude. Everybody with me so far? And then I can rewrite this, just rearranging things. I want it to look like now just the integral over d cube r prime. And I can do that if we take the phi 2 r prime and rho 1 r prime. So you could think of this two charge distributions and their total electrostatic energy as rho 1 in the field created by rho 2 or rho 2 in the field created by rho 1. Does that make sense? Everybody with me? Okay, so there are this reciprocity relation that exists, right? So the total electrostatic potential energy VE is d cube r rho 1 r phi 2 of r, or it could be d cube r rho. What am I saying here? Okay, yeah, let's see. I think what I wanted to say is already there. So what we are going to do now is we don't have much time, so I don't think we will be able to complete the discussion of the problem. So we will leave it at that, as you know, that will also give us an opportunity to connect with this topic again. So we will take a look at an example of this reciprocity relation and its application in the class on Thursday. And at that time, then we will be done with chapter 3. We will start looking at chapter 4. Once we're done with chapter 4, which is the multipole expansion. So you already know some of that. So we won't go through all the details there. And then I'm going to bring in magnetostatics so we could kind of see the parallel between the two before we start discussing other techniques for calculating electrostatic and magnetostatic fields. Okay, so that's it from my side today.